Hello, guys, and today is our second lecture for the acid base balance, and the contents are the buffer system and its explanation, the action of the buffer, and there are quick questions like examples. Okay, so let's get started. First of all, the buffer system, as we have discussed a little bit in the previous lectures, that the buffer system is there to resist a pH change. Okay, the buffer system is present in our blood to resist the pH change. It maintains the pH within the physiological limits. So let's discuss about it. First of all, we have discussed that buffer can be exist in two forms. Okay, it is in protonated form and in the non-protonated form. Protonated form means that a hydrogen or proton is attached to it, okay? And non-protonated form means that hydrogen or proton is detached from it. But we need to understand that a good buffer system must have both the protonated form as well as the non-protonated form of the buffer. In this condition, it will act as a good buffer, okay? And we have discussed that the pH is basically negative log of hydrogen ion concentrations. Okay, pH is equal to negative log of hydrogen ion concentrations. And we have discussed that hydrogen ion concentration is how we derived the value for pH and what basically is hydrogen ion concentration. One most important equation, or we can say a relation, is known as the Henderson Hassel Balch equation. And this equation is a mathematical representation and it represents the relation between pH, pK, and ratio of ion concentration. First of all, it is showing us the relation between the pH of a solution, the pK, okay, the coefficient, and the ratio of the ion concentration. We need to understand this, okay? So let's derive together the Henderson Hassel Balch equation. So first of all, if there is a solution, as you can see that this is a solution and it contains a buffer, okay? And Ha, the protonated form, is reversibly in relation with non-protonated form, okay, H positive and A negative. It means that both H positive, Ha, the protonated form, and this, the non-protonated form, is present in a solution. So let's talk about it. We can write Ha concentration and the forward constant is equal to H positive concentrations and A negative concentrations, and then we can write as the reverse constant. This is like a basic or fundamental representation of Hassel-Balch equation, okay? So in order to remove these arrows, we need to add something equal or something that can in written in place of these arrows. So K1 is K1 multiplied by HA is equal to K2 multiplied by H positive concentration and A negative concentrations. When we take the K2 on that side, it's K1 by K2 and the HA is going to divide by H positive and A negative. It's like common sense, okay? And in place of K1 and K2, we can write a big K. That's what is PK, and we are going to write it as PK later on, okay? We can write K1 by K2 as capital K, and the rest is the same. We need to find the hydrogen ion concentration, okay? We need to find the hydrogen ion concentration, so we can let the hydrogen ion where it was and take the rest of the things on the opposite side. When this division goes there, it multiplied, and this multiplication changed to division, okay? And this is like a structure. This is like going to get our Hassel-Balch final equation, okay? So in this condition, or in that time, we need to multiply the both sides by negative log. It's negative log, it's not the positive log. It's very important to remember, we need to multiply both sides by negative log. Here we multiply negative log, it becomes negative log into hydrogen ion concentration. It's simple. And on this side, when we multiply negative log, it becomes negative log K minus negative log HA by A negative. It's like coming in like minus forms. Okay. In the previous lecture, we have discussed that pH is nothing but the negative log of hydrogen ion concentration. So in place of negative log of hydrogen ion concentration, we can simply write pH. And do you think that we have written minus log into P? Yes, we have. So in this condition, we can also write negative log into P. And from where we get the pK, it's very clear that from negative log of K, we get the pK minus log HA by A is equal to pH. And that's the final form of our Hassel Balch equation. Its pH is equal to pK, but from where the positive sign has come, because it's negative sign. So how are we gonna deal with the negative sign? We can just change it into positive, and when we change the negative log to positive log, the front equation is inverted. Okay, so A negative comes numeratorily and H positive become the denominator and is equal to pH. So what's the final final equation? Its pH is equal to pK plus log of A negative by HA positive. And this end equation is applied to solutions with buffer system. We can apply this equation to a buffer solution and we can find the pH of the solution, we can find the pK of the solution, we can find the ratio of ion concentrations. So first of all, we can apply this equation and then we will move forward. Example number 1 is that if the reaction constant pK, A negative and H are known, we can find the pH. We can find the pH when we have these three known values. It means that in the place of pK, we can write 6, log A is 100, and by 10, the log 100 is 2, and 6 plus 2 is 8. So when we know the ions, when we know the ion values, when we know the reaction constant, we can find the pH, and that's what exactly we have done here. Example number 2 is that when pH and pK are known, we can find the ratio of H and A, H and HA. It's not H, it's A and HA. We can find the ratio of these ions. So let's do it. pH is 5 and pK is 6 plus log. So 6 goes to the other side, it becomes -1 and log remains same, A by HA. And now what we are going to do, it's like that we take the anti-log on both sides. When we take the anti-log on both sides, this side is cancelled with the log and this side becomes 0.1, and we can write the 0.1 as 1 by 10 is equal to A by HA. So when we know the reaction constant and the pH, we can automatically find the ratio between the ions. And the third example is that if the buffer system has equal concentration of protonated and non-protonated form, it means that when A negative and HA positive, these are equal. Okay, when these are equal, it means that the pH of that solution is exactly equal to the pK. So let's find it. How? pH is known, pH is 7.4 and pK is to be found, and plus log, it means that we can place any number in place of H and HA and A because these are same. Log 1 is 0, and that's exactly when we get pK is equal to pH. pK 7.4 and the pH was also 7.4. From here we conclude that when there are same concentrations of H and A, it means that when there are same concentration of protonated form, the protonated form and non-protonated form, we can assume, we can comfortably say that pK of that solution is equal to pH. It means that this solution is same pH and pK. For example, in this container there are three buffer systems, or we can place them in different containers as well. So it means that the protonated form and the non-protonated form are equal in number, and assuming that we know the pH of this system, so then pK is also 3. Here the pH is 7, and considering that both protonated and non-protonated form are equal number, so pK is also 7. This pH is 6, so pK is also 6, okay, when there are same concentration of A and HA. So, talking a little bit more about the buffer system is that what is a good buffer? Good buffer is a buffer system in which half of the molecules are in protonated form and other half are in non-protonated form. It means that, for example, we can take example of blood. Okay, there is blood of a patient, or there is a blood of any animal, mainly a biological system. Okay, pH of the solution became acidic. We are adding, or we are injecting hydrogen ions into that fluid or into that blood. It means that pH of that solution or that blood starts to decrease because hydrogen ions are increasing. Okay? So a good buffer is that it has half protonated form and half unprotonated form. What does it do? It will cause the unprotonated molecules to capture the additional hydrogen ions that we have added. Okay, it will capture those hydrogen ions that we are adding, and it will resist the pH fluctuation. On the other hand, in the same blood or in the same solution, we starts to add the alkali, for example OH. The OH will combine with the free hydrogen in the solution and forms water. Okay, and those free hydrogens which are maintaining our pH has been converted to water by OH. So pH starts to increase, but what the buffer will do? Buffer has protonated system and an unprotonated system. The protonated molecule of the buffer will start to donate its protons to like maintain the pH of the system, okay, to maintain the pH of the fluid. So protonated molecules will start to donate their hydrogen ions, and they prevent the pH fluctuation. Okay, so what we conclude from it? We conclude that buffering system works very excellently when half of the molecules are protonated and half of the molecules are non-protonated. It means that, what does it mean? It means that half of the molecules are protonated and half are non-protonated. This, in other words, mean that pH of that solution is very close to pK. We have discussed that protonated form and non-protonated form, when they are equal, it means that pH of that system is equal to pK. And in other words, we can say that when HCl or acid is added to a buffer solution, the buffer will accept the extra hydrogen ions. Okay, and when the alkali is added, the free protons will form OH with water. Okay, it means that the OH added will react with the free protons present in the solution and they form water, and pH starts to increase. But buffer role is to donate their extra protons that what they had in the protonated form. Okay, but after saturation, it means that when the buffer system is saturated, they can no longer take the edge and they no longer can donate the protons. Here the problem comes. After saturation, more addition of acid will make the solution acidic, and after the saturation, more addition of alkali will make the solution alkali. Okay, and there is something you need to know, that buffer system works maximally at the pH range from 6 to 7, okay, 6 to 8, in which the buffer has half protonated and half unprotonated forms. When pK and pH are different, buffer activity declines. We know that when pH and pK are different, it means that they have a difference of a lot of units. For example, pK is 7 and pH is 2. So how that buffer system is gonna work accidentally? No, it's not gonna work accidentally. Its activity starts to decline. Buffer system can work properly when pH is within 1 unit of pK. For example, pK is 6, so pH is 7, or pH is 8, so pK is 7 or 9. Okay, 1 unit change can be bearable. Okay, it's the graphical representation. So let's see what is happening. The green line shows that when protons are added into a non-buffered solution, okay, protons are added to a non-buffer solution, it will cause an extreme and very erratic change in the pH, and pH starts to change very rapidly. Okay, adding protons in the non-buffered solution, this, so when we add the proton, the pH starts to decrease very rapidly because there is no buffer in the system. But when we add alkali to a non-buffered solution, its pH will decrease drastically in no time. But here, the blue line, when we add protons or acid in a buffered solution, the pH, they will resist the pH change. When we add a lot of protons, pH is still the same, and after the saturation, the pH starts to decrease. And when we add alkali in a buffered solution for a long period of time and large amount of alkali, it will resist the fluctuation in pH, and ultimately after saturation the pH starts to increase. And this graph exactly shows that what buffer is doing and what is the function of buffer. So I hope you understand the Henderson Hassel Balch equation as well as the functions and concept regarding the buffer. I will see you in the next video. Till then,